Okay, welcome to today's session on the fourth week of the Computational Fluid Dynamics course offered on NPTEL. I'm Shankar H, and I'll be taking this session from 6 o'clock to 8 o'clock to clear all the questions and doubts that come up. So this week's assignments, or week three's assignments, the graded assignments of week three were related to a rectangular duct problem, and which has a width W in the x direction, height h in the y direction, and length L in the z direction. I think I missed that out over here. There's a length L in the z direction, and all the questions are related to this particular statement over here. So before I continue, if you attended any of the previous doubt sessions that took place yesterday or last week, I think it will be more or less covering the same ground on that. So if you want to focus on something else, you are free to do that. If you want to stay and have any questions cleared, and you can welcome to do that as well. So
looks like I'm alone today.
yes. So let us consider the steady flow of a fluid through a duct of rectangular cross section with width W, height h, and length L. And we say that the planes A and B are at length 0 and L distance apart. So I'll just mark that over here. So from A to D, the length is L. And it is given that the planes B and C are a distance of 0.5 and 0.9 times the L. So from A to B it's 0.5 times L, and from A to C it's 0.9 times L. This is the problem that we have been given. Now we have to say that the velocity profile at the inlet is uniform, so when it enters at a particular velocity all throughout this cross section, and the length in the z direction is much more than the length in the x and y direction, the dimension in the x and y direction, and one can expect the flow to be fully developed by plane C. So after 90% of the length is covered, only then will the fully developed flow be occurring. So for such a system, first question is regarding, we wish to calculate the velocity and pressure field for a laminar flow of water at 20 degrees Celsius through the domain shown in figure 1. And the first question is, how many partial differential equations do we have to solve?
It would be 4.
Yeah, it is 4. The first equation will be the continuity equation. Since this is a steady state problem, we can write it as del dot u is equal to 0, and we can assume that even if we are solving for an incompressible fluid, we'll get del dot rho u equal to 0, and then we'll get 3 equations from the momentum balance. This is regarding the mass balance or the continuity equation. And we'll get second, third, and fourth equation from momentum balance as follows. In the vector form, it can be written as du by dt should be equal to minus 1 by rho del p plus mu del square u plus rho g, where u and g are the vector component in the vector form. So in 3 dimension we'll get 3 equations, and we solve for 4 unknowns. Pressure,
Mass
sorry,
balance will always be 1, right? The continuity
Uh,
equation will be only one at all times, right?
yeah, mass balance, since it is not in a vector form, since it's a
Correct.
scalar, we don't
Correct.
have to worry about the component in each direction.
Right.
So we just worry about a single equation that connects the mass balance for such a problem. And then we come to the velocity in the x, y, and z direction, component momentum balance. That we worry about three equations. Moving to the second question, if the width W is 0.04, H is 0.03, L is 1.5. We need the inlet velocity for an inlet Reynolds number of 1000. And what we, I think I have missed out a couple of things. What we have assumed here is for water. That's one statement I am writing it here right now. So basically, any equation that relates the Reynolds number is given by rho v d by mu. So v is the velocity, rho is the density, d is the characteristic length, and mu is the viscosity. Now, how would we define the characteristic length and which velocity should we take is an important question of concern here. Now, it is given that there is an inlet velocity of 1000. So, we have to assume that the flow happens in this direction. So, the given velocity is in the z direction, and what they have given is not w, not omega, or the component in the z direction, but Reynolds number, which is characterized by a flow in the z direction, is given as rho times w times b by mu. But again, we need to for now find out what this d stands for, and for any general case, we have to define something known as the hydraulic diameter, which is basically the uh, the total surface area divided by wetted perimeter.
Mr. Shankar, I'm sorry to interrupt. Uh, is are we today was supposed to be week 4, right?
Yeah, we are doing week 4, but I can't discuss the graded lectures of week 4. So I am doing the graded assignments of week 3, then moving on to the non-graded assignments of week 4. The graded
But week
assignments
4,
of week 4 will be discussed in the week 5 class.
because week 4 is already graded, correct?
No, week 4 is yet to be graded.
No,
Is
it's done.
I thought it was due date was around 12th or something, or sorry, 1st or something. Am I
No, hold
mistaken?
on. 1 second.
Week 3 is due on 15th.
No, week 4 is due on 22nd. Because I remember going through this last week. What you're talking about now?
I see. I guess I am 1 week behind in uh, the classes actually. I
Oh,
guess one of the TAs would be ahead and the two of them would be lagging up by a week. I
okay.
think that's the case. I'll just check with the others and catch up if required.
So no. So today will you be doing week 4 at all?
I'll be touching the non-graded assignments of week 4. I won't be doing the graded assignments.
And tomorrow?
I'm not sure. I think we may. I have. I think I needs to be checked out. I'm not sure what the content has been prepared for by the TA over there.
Because I didn't attend yesterday and day before. I thought it would be repeated today. So I figured it. Yeah.
I was under the assumption that week 3 has to be done today. I have not done week 3 last week, so I've done 1 week prior. Actually, I think the TAs allotted for Mondays and Tuesdays timetable will have 1 week lagging. I'm not exactly sure. I think it needs to be checked out. I'll verify it next week in my class. I think it's best if you can take a look into tomorrow's lecture if you want to
Because
verify it for yourself.
on the top you've written the week 4, so I got confused.
No, it's week 3. Graded assignments for week 3 is what I've
No,
written.
on the top of your. Uh,
Yeah, just this is the
ah,
week 4's live session.
okay.
Yeah, week
So
4 live
so
session
yeah.
deals with graded assignments for week 3 and
Okay.
non-graded assignments for week 4. Because this
Okay.
is the fourth live session I am dealing with.
I see.
So
Okay.
based on my calculation, I have to do the graded assignments for the previous week.
I see. Okay. So if you don't mind, I will exit because this is a repeat for me from last week. Last week.
Sure, 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 sure.
Thank you.
Okay, as I was saying, I'm dealing with the total surface. We have to define something known as the hydraulic diameter, which is given by 4 times the hydraulic radius, and the hydraulic radius is given by total surface area times the wetted perimeter. Therefore, a for a rectangular cross section of, let's say, length A and height B, we will get the hydraulic radius to be equal to total surface area will be A by AB, and the total wetted perimeter would be A plus B times 2. Therefore, the hydraulic diameter will be equal to AB by A plus B times 2 times 4. Therefore, we'll get it as 2AB by A plus B. Now here the length and height are given. L is equal to, I think, 0.015 and H is equal to 0.024 meter. Let me just confirm that. Oh, sorry, 0.04 and 0.03. So this is what's given to us. We don't have to worry about what's there in the z direction, since that is not what is coming in the characteristic lengths equation. When we find the characteristic length, we only have to deal with the cross section that the flow happens through. Yeah, I can see your message. Hi, Veera. You can find the previous lectures on the Swayam website. There will be at the bottom of the course topics, you'll be seeing a problem solving lectures. And in that, I think you'll be able to uh, find the recorded lectures, the YouTube link for the recorded lectures. Um, it's in the Swayam website. I mean, how do I share this to you? Okay, one second. Let me see if I can get that for you. It's there in the Swayam website. See if you are able to access this. Yeah, sure. So moving on to the finding the hydraulic diameter, we'll substitute this into this equation. We'll get this as 2 times 0.04 times 0.03 by 0.07. I think we come here, and we substitute this hydraulic diameter equation into the equation for Reynolds number to find it as rho times V times dH by mu, and Reynolds number is given as 1000, density is again 1000, velocity is what we have to find, or we just keep it as the notation used for this question W. times hydraulic diameter is 2 times 0.04 times 0.03 divided by the viscosity of water is 1 centipoise times 0.07, that comes from here. And when we solve this question, we'll get the answer, I think, as A, 0.03 meter per second. So moving on to question number 3, we'll have to write the continuity equation for this particular case. And the continuity equation in the vector form is written as del dot rho u is equal to 0 if we assume incompressible flow. We'll get del dot u is equal to 0, which deals dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap dotted with ui plus vj plus wk should be equal to 0. So we'll get dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. And this is the answer. I think answer option C will come. Sorry about that. Moving on to the next question, where we deal with the steady state momentum balance in the x direction and which among these equations is properly given by them. So we saw that the momentum balance in the vector form is given by du by dt is equal to minus 1 by rho del p plus mu del square u plus rho g, and this u and g are in vector form. Therefore, when we write the component balance in x direction, we are basically writing this as the substantial derivative is basically written in the component balance as du by dt, the unsteady term, plus u du. Now let's make this all as partial differential, because since u is a function of x, y, z and t in a general sense, we can write this in the partial differential form as u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Now this term will come here, therefore that will be minus 1 by rho dou p by dou x, plus this term will come after that, that would be given by, sorry, there's a small mistake in one of the equations I written. It will be mu by rho times dou square u by dou x square plus dou square dou square u by dou y square plus dou square u by dou z square plus rho into gx, the component of the gravitational force in the x direction, and this is basically the momentum balance in the x direction. Therefore, among the options that's given here, although none of this have a does not have a gravity term, we can assume that there is no gravity in the problem that we are dealing with, and among whatever that's been given, we can assume that a steady state momentum balance is asked, or it's given that steady state momentum balance. Therefore, the correct answer is option C. Now, moving on to the fifth question, we have to take a look at the plane D, where a fully developed flow has already been reached, and that is at a distance of z is equal to L. We are looking at plane D, and at that point, for a fully developed flow, we know that the pressure gradient in the direction of flow should be equal to a constant, and there is no other constraint about the pressure variation in the x direction or y direction. Therefore, the pressure gradient does exist in the x direction. It's not zero, because there is a velocity, a parabolic velocity profile that's developed towards the end of uh, the plane, the boundary given here. Therefore, there is a variation of pressure in the x direction and y direction, but not in the z direction. Second point is the variation of velocity with respect to the z equal to 0. that statement is correct, as there is uh, no change in the z direction after the fully developed profile is obtained, and that's how we define the fully developed flow as the condition in which there is no variation in the axial direction or in the flow direction, only variation along the boundary conditions, along the boundary phenomena. And the velocity at the point of exit is the same as velocity at the point of inlet. That is again false. It will be usually be higher than, it depends on the point at which we are being looking at. If you are looking at the boundary, then it will be a no slip condition. That means its velocity is zero. If it's at the center, it will generally be higher than the inlet velocity because a pressure is being applied over the entire thing. So this is again wrong. The next question deals with the statements about being true about the pressure at the midpoint of plane C. And plane C is when the fully developed flow has happened. And at that point, if pressure at point C is greater than pressure at point inlet, if this pressure is less than pressure at point C, then we won't expect the flow to happen in this direction. We expect the flow to be in this direction. Therefore, option 1 is in fact wrong. And if for a fully developed flow, we can say that the dou P by dou Z is equal to constant. But since this is at the point of fully developed flow, we have just assumed that at point C, the fully developed flow starts to form. Therefore, dou P by dou Z is not a zero. If there is no pressure gradient, there won't be any flow. And dou P by dou Z is also not a constant. It only constant for a fully developed flow. Since this is at the point of fully developed flow, it won't be zero, it won't be constant. Moving on to the next question, which of the following true statements is true about the velocity at the midpoint of plane B? So we consider plane B, which is at a distance of 0.5 times the length. Let me write that down. This distance from A to B is 0.5 times the total length. And here what is asked is yeah. So since we have been asked about the velocity at point B, we see that for the flow to happen in this direction, we need that velocity B should be greater than the velocity at inlet. So this first statement is false. In the portal, in the Swayam website, it's actually given as WB is greater than V in, and that statement is true. Then is there a gradient along the z direction at the plane B, and or is there no gradient? We know that in this fully developed regime or fully developing regime, we see that there is a gradient in the velocity, and we see that this is again a false statement over here. And that gradient is not exactly a constant for the velocity. It changes in a linear or a, sorry, non-linear manner. We initially get this boundary which turns slowly into the fully developed flow, and this is how the flow develops. So it's not a constant gradient in the z component of velocity or the w at the plane B. So moving on to the next question, which of the following is true for a Newtonian fluid? And we know that for a Newtonian fluid, for the case of a Newtonian fluid, we know that the shear stress is proportional to uh, the rate of strain, rate of shear strain. Let us assume this is tau x y, then it will be du by dy, or it will be tau yx, sorry, should be equal to du, proportional to du by dy, and the proportionality constant is given by the viscosity. For a Newtonian, this is known as the Newton's law of viscosity. In viscosity, it's called Newton's law of viscosity, but this is the Newton's law in this context. So we see that the viscous stress is not proportional to the strain, it is proportional to the rate of strain or the strain rate. Therefore, first option is wrong. And second option is viscous stress is proportional to local deformation rate, and this local deformation rate is also known as strain. Therefore, this statement is also correct. This statement is correct. And third point is viscosity is independent of shear stress, as we see that viscosity is added as the proportionality constant. Therefore, for the Newton's law to be verified, or for the Newton's law to hold valid, we have to assume that the viscosity is independent of shear stress for a Newtonian flow. So, moving on to question number 9. For a steady laminar fully developed flow of an incompressible fluid between two infinitely long wide parallel plates undergoes which type of strain? Basically, it's the correct answer would be rotational and shear, but not extensional, because the rotational strain is given in about the x-axis by half into dou v by dou z minus dou w by dou y. Let us assume that the flow is happening in the uh, y direction here. So flow is happening in the z direction and is a function of y. So let us assume this to be our x-axis, this to be our y-axis, and this to be our z-axis. For a flow between two infinitely long wide parallel plates, w will be a function of y. So we can find that the dou w by dou y will not be equal to 0. Therefore, the rotationality omega x will be not equal to 0. There will be a rotationality along the x component. Extensional rate of extensional strain is given by E uh, XX, E YY, and EZZ, and all of them have the formula of dou W, or this will be dou U by dou X, dou V, sorry, dou V by dou Y, and dou W by dou Z. And we see that W is a function of Y only. Therefore, U and V are equal to 0. So this will be 0, this will be 0, and this will also be 0. Therefore, no extensional strain will exist. And shear strain is given by tau x. Let's assume it as tau yz will be half dou v by dou z plus dou w by dou y. And we again shown that w is a function of y and u and v is 0. Therefore, epsilon yz will have some component as w by dou w by dou y. Although all the other terms may be 0, including dou xz, dou zx, and dou xy and exy and everything else will be 0, there will be a certain component in this shear strain. Therefore, shear strain will not go to 0. There will exist a term for shear strain. Moving on to the 10th question. For a fully developed flow, the steady state momentum balance equation reduces to which among the following? And we saw that the steady state momentum balance equation is given by, oh, excuse me about that, is given by dou u by, or let's assume it's a w direction, dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z should be equal to minus 1 by rho dou p by dou z plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. For a fully developed steady flow, we see that this component goes to 0, this component goes to 0, and since w is a function of x comma y for a two-dimensional flow, we can say that, and u and v are equal to 0, we can say that this term, this term goes to 0, this term goes to 0, and since w is not a function of z, this term goes to 0. Therefore, a pressure gradient will exist, and w is not a function of z, so this term again will go to 0. So we get the equation as dou square w by dou x square plus dou square w by dou y square should be equal to minus mu by rho dou p by dou z. Now, moving on to the last question for the graded assignments for week 3. This question I have kept as an extra question, and this basically the same question that I have discussed before. If the width of the channel is 4.04 meter and the height is 0.024 meter, what is the velocity of air given the density and the viscosity for an inlet Reynolds number of 1000? Again, we define the hydraulic diameter as 4 times the hydraulic radius, and hydraulic radius is 2ab by the surface area by the wetted perimeter. So this would be 0.04 times 0.024 by 2 into 0.04 times 0.024. Therefore, we'll get dH is equal to 4 times RH, which I think we should get the answer as 0.03. Maybe a further calculation would be needed to verify this answer, but I think the answer is 0.03 in SI units. And we substitute here, we substitute this value in the equation for the Reynolds number given by rho u dh by mu, which is equal to 1000 For air, it's 1.2 kilogram per meter cube, and we are finding the velocity. Hydraulic diameter is given by 0.03 meter, and the viscosity of air is given out to be 1.8 into 10 raised to minus 5. And when you solve this equation, you will get u to be 0.5 meter per second. That is option B. Moving on to the non-graded assignments for week 4, which deals with catalytic reactions or CFD for reactions. We solve for the flow in a reactor in which CO, carbon monoxide, gets converted to carbon dioxide, and the production of hydrogen which is known as the water gas shift reaction, and follows this equation: CO plus CH2 giving CO2 plus H2. Let us assume a simple configuration for this reactor. See the figure that's here, and this figure is what being talked about. The multi-gas mixture flows through a rectangular channel. Due to its reaction, its composition changes from the inlet to the outlet. Let us assume that this is the inlet and this is the outlet. The top and bottom walls of the channel are coated with the catalyst, and two side walls are used to heat up the gas to the desired temperature of 200 degrees Celsius. For a given flow rate of air with a given concentration of the four gases, for given side wall heat flux and given catalyst surface area. So flow rate is given, gases concentration is given, side wall flux is given, and catalyst surface area is given. We wish to calculate the percentage conversion of CO to CO2 by the time it reaches the end of the channel. And we want to find out using the CFD simulation, assuming steady laminar first order reaction kinetics for the reaction, and we have to answer the following questions based on this. Which of the following needs to be specified for statements is true about the rate of about the chemical reaction? So we just need to find out what all needs to be specified. We know that when we solve the equation, we will be solving the equation for a species balance equation. We will be dealing with an overall mass balance. We'll be dealing with we don't have to worry about the okay. We'll be dealing with the mixture continuity equation, and which is these both are the same. Then mixture momentum equation, and finally energy equation. And among all of these equations, only the reaction kinetics and heat of reaction need to be specified. We don't have to worry about the rate of reaction, because the rate if the reaction kinetics is given, we'll be able to find the rate of reaction at all the points throughout the domain. Whereas if the rate of reaction is given, it will be at a particular point and it will be difficult to, it won't be possible to find out using CFD simulation. So what we need is the reaction kinetics and the heat of reaction. Which of the following do we need to specify about the catalytic reaction? Whether we need to specify the activation energy, catalyst surface area, order of the reaction, or the reaction mechanism. Now, for a catalytic reaction, we need to mention what the uh, energy of the reaction is. Therefore, the activation energy is a required parameter here. The catalyst surface area is also a parameter for calculating on what for in the mass balance and the energy in the energy balance. We require what the catalyst surface area is to in order to properly compute what the uh, mass of reaction or the rate of reaction is coming to out to be. We also need the order of the reaction, and therefore we don't need the reaction mechanism, because if the order of the reaction is specified, we would know how the reaction mechanism may happen, and we just have to go through with how the reaction order goes out to be. Now, how many mass conservation equations do we need to solve? So basically we have four. In this particular case, we have CO, H2O, CO2 and H2. Therefore, four species are there, and we will get four species balance plus one overall balance, or let me call that as mixture balance. Now we see that when we solve these five equations, we see that all five of them are actually dependent on each other, such that if we construct a matrix out of these mass balance, we'll get only the rank of the matrix to be equal to 4. Therefore, we need to solve four mass conservation equations when we are dealing with this problem. Next, if we assume the flow to be three-dimensional and the total number of partial differential equations that needs to be solved is how much? So we will have the number of species ns minus 1 times the species mass balance, that's equal to 3. We'll have one mixture mass balance, it's equal to 4. Sorry, it's equal to 1. We'll have 3 momentum balance in x, y and z coordinates, so there'll be 3 more, and 1 overall energy equation. Therefore, we'll get a total of 8 partial differential equations that needs to be solved simultaneously when we are dealing with this problem. Okay, we'll move on to the next question where we ask the rate of reaction appears in which of the following conservation equations. For that, let us first write down each of these four equations. First, let's start with species mass balance, and that is given by dou times rho I by dou t plus del dot rho I times u is equal to del dot ji plus ri. And this would be the unsteady. The first term would be the unsteady term, the second term would be the advective term, the third term would be the diffusive term, and the fourth term would be the rate of accumulation or generation. So here rate of reaction needs to be specified. When we deal with the mixture mass balance, we just write dou rho by dou t plus del dot rho u is equal to 0. We see that no rate of reaction is not mentioned anywhere here. Only the incompressibility density will be mentioned here along with the velocities. When we deal with the mixture momentum balance, it is given by dou u by dou t. Here will be a vector plus del dot u should be equal to minus 1 by rho del p plus mu by rho del square u plus g. And here also rate of reaction is not specified. Finally, if we deal with the mixture energy balance as given in the fourth statement, we'll be writing that as rho times Cp times dou T by dou T plus rho Cp del dot Ut should be equal to K times del square P plus mu times phi V plus Qr. And in this Qr, we'll be dealing with the heat of reaction, and that is actually dependent on the rate of reaction. Therefore, rate of reaction appears here as well. Therefore, the correct answer is species conservation and mixture energy conservation. Mixture mass and mixture momentum conservation does not have the rate of reaction term. Okay, so I guess that's all the questions that we have planned to discuss. I think I will end the meeting over here. If you have any other questions, please reach out to me for the next Monday's session at 6 o'clock to 8 o'clock. I thank you for your time and attention, and see you next week.